Hello class, this is CSE-4600, Section 1, Week 5, Spring 2025. Alright, now, before I even give you instructions on what your first project is gonna require, I would like for us to talk about CPU scheduling. So for those of you who were in the Tuesday in-person class, or just need a refresher, let's talk about CPU scheduling, okay? Alright. Okay, so this is an important aspect so CPU scheduling is an important aspect of an operating system. We have the idea of a process and accompanying that, we have the concept of a process and abstraction of a running program. Accompanying that is the concept of a thread, which is a different flows of different threads of execution that are within one program. If one thread is blocked because it's waiting for input, some other part of the program could run instead. If, for example, you are in a garden and someone's using the garden shears already, you could do something else, such as turn the compost pile, for example. Okay, so the CPU scheduler or scheduling algorithm that decides which process gets to run next on the CPU. This applies to an extent to threads as well. The early days of batch systems, in the earliest days of batch systems, the next job was literally to just run the next job on the tape. Back in the second generation of computing, you would have people submit a stack of punch cards to a card reader. This would then upload your job onto a tape. Once several people's jobs were uploaded to the tape, it would be brought into the mainframe to be computed, and then the results would be written onto an output tape. So literally it's just there really is no scheduling algorithm. It really is just run the next job. That's it. Eventually, this output tape would be taken to a printer, and then it would print out the results. Multiprogramming makes this more complex because there are multiple users waiting for service. And the introduction of personal computers makes this a lot different in two ways. Most of the time, there's only one active process, and we've reached a point where the CPU is rarely a scarce resource. Even if you ignore the fact that we have multi-core CPUs now, the limiting factor for most personal computers is not how fast the CPU can get jobs done, but how fast it even gets input from the user. Unless you are rendering a 3D movie, and you might be, for, say, an art project, unless you're rendering something on your computer, like 3D rendering, typically the bottleneck for a personal computer is how fast it gets input. Which, in a way, is a counter-argument to getting the best of the best CPUs out there, like the Ryzen 7 and Ryzen 9 and Intel Core i7 and i9. On network servers, multiple processes are competing for the CPU, so scheduling matters. On mobile devices, you're limited by what can fit in the form factor of your phone, and also how long the battery can keep things powered. And finally, the act of switching between processes. So we talked about the concept of pseudo-parallelism, where the CPU on a single core computer switches between processes very fast to provide the illusion of running multiple programs at the same time. That action of switching between processes, which is called a context switch, it's an expensive operation. There's several steps. The system must switch from user mode to kernel mode. The state of the current program, or I should say the state of the current process, is saved. Whatever is written in all of the registers on the CPU, we must save all of that. There might also be information regarding the memory for that process as well. You gotta save all that too. And once we have that saved, we load another process by loading its saved state information back into the registers, back into memory, and then we run the process again. And once that time is up for that process, we repeat these steps for another process. We can roughly categorize processes by how much computing or waiting they're doing. If they're doing lots of computing, we call these processes not IO bound, compute bound processes. So these are processes that are doing a lot of work. They're doing a lot of work. They're doing a lot of computing. The reason that they stopped is because for example, ran out of data to process, and they have to wait for say the hard drive to read more data from the disk and load it into memory. Or maybe it's asking the user for user input and it's waiting for the user to type in something. So that's what we mean by waiting for I/O. It ran out of stuff to do, and it's waiting for more stuff to be processed to come in. We can't do a job if we don't have work we can't do a job if there's nothing to work on. Conversely, if there's a lot of waiting, we call that I/O bound. So here a CPU is spending more of its time waiting for I/O. This could be, once again, waiting for user input. Maybe it's one of those programs where it's just sitting there waiting for user input, so it's basically doing nothing. A program that's waiting for user input, maybe this could be a program on an ATM. Or maybe you just have a web browser running in the background, it's just waiting for user input to do something else. But anyway, we call these I/O bound processes because they are just doing more waiting for I/O. Or maybe this could be a program where it's processing data so fast that the bottleneck is keeping it fed with data to process. And that's a paradoxical thing. The faster we make our CPU, the more likely it's gonna become the faster we make a CPU, the more likely it is to become I/O bound. Because yeah, you give it work, but work's all done. I need more data. Yeah, give a CPU some work, process it all up, and it's all done. And it's just sitting there waiting for more input. So yeah, we characterize processes by how big their CPU bursts are. Compute-bound processes have these large CPU bursts, or I should say long CPU bursts. I/O-bound processes have short CPU bursts. There are a variety of situations in which we need to determine which process to run next. When we create a process using, say, the fork system call, do we run the parent first? No, do we run the parent or do we run the child? When a process exits, which process do we run next? When a process blocks on I/O, which process do we run next? And when an interrupt occurs, that means an I/O request a process has completed, and the process that had made the request is ready to run again. So when a process is blocked, it might be removed from the CPU so that another process may run instead. When the process that was waiting for I/O, when that I/O interrupt occurs, it's basically telling the system this process that had made an I/O request has been completed, and now it is ready to run again. Do we run that process next, or do we run some other process instead? So that's the question of when do we schedule processes to run next? There's a simple way we can do that, and that is to say, let's just cause an interrupt every, say, 10 milliseconds. Or maybe, let's just say we have a clock that goes off every 2 milliseconds, and every fifth interrupt, we make a scheduling decision. So, we have a clock, tick, 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 tick. Okay, now we need to make a decision of which process runs next. So, there is one way we can do this, and say every 5 clock interrupts, we pick another process to run. So, if you can imagine a line in which processes fall into, there is a line for process. There's a line to the CPU. Processes line up in that line. We call it a queue, by the way. So processes are queued up for the CPU. They run one process at a time from the front of the line. It runs for 5 clock interrupts, and at the 5th clock interrupt, that process moves back to the line, and the next process in the front runs on the CPU next. 5 interrupts later, that process is removed, goes back to the line, and the next process in line runs next. That's called round robin, and that is what is called a preemptive. That is what is called a preemptive scheduling algorithm. We run processes for some amount of time. After that, it's removed from the CPU, goes back to the line, and we run another process next. For this to work, we need a clock interrupt. If we don't have a clock giving us clock interrupts periodically, then the only option available to us is to use a non-preemptive scheduling algorithm. In this case, we let a process run, and we let it run until it finishes its job. If we don't have a clock, this is our only option. So preemptive scheduling algorithms, for our discussion, they let processes run for some amount of time, and then they run another process after that, a different process after that. Non-preemptive, we have no means of preempting the CPU from a process. So the process keeps the CPU for however long it needs to run. There are several different scheduling algorithms for different environments. Regardless, there are some goals that we want to meet. So, for example, we want a scheduling algorithm to be fair, we want to enforce that policy, and we want to make sure all parts of the system are busy. That's for all systems. So, fairness, comparable processes should get comparable service, except in cases where we have a high priority process. It's not uncommon to have such processes. Sometimes you're going to have idle processes wasting space, so whatever resources they have, you can just deallocate them. If these are processes that aren't doing anything, you can save their state onto the disk. And then the memory that you have freed up that way, you can reallocate it to processes that need that memory. So that's fairness, or rather lack thereof, because we want to give processes roughly equal treatment here, except for when we have a high priority process. Policy enforcement, we need to enforce whatever policies are on a system must be enforced by the CPU scheduler. And oh yeah, keep the CPU and related I/O devices busy. More work gets done if that's the case. For batch systems, the more jobs we can get through per unit time, the better. Turnaround time, the faster we can get a job done from the moment it was submitted, the better. So high throughput is better, lower turnaround time is better, and for CPU utilization, it's more than just keep the CPU busy. It's also a good metric for knowing when it's time to upgrade your system to something more powerful. There are some caveats regarding that. If you have a batch system scheduling algorithm that is designed to maximize throughput, and you have jobs of large sizes, if you have large jobs and small jobs, it might be the case that it'll just prioritize all the small jobs at the expense of all the large jobs. Fair for the small jobs, not fair for the large jobs. So, if you want a good scheduling algorithm for a batch system, you don't necessarily want to maximize. You might not want to maximize, or I should say minimize, turnaround time. Because if we want to minimize turnaround time, let's just do all the small jobs. And no work gets done on the large jobs. So for this reason, a scheduling algorithm that maximizes throughput may not necessarily minimize turnaround time. In fact, if we are maximizing only turnaround time, we are only just doing small jobs. Response time, lower is better. Proportionality, these are for interactive systems, by the way. Yeah, so response time and proportionality. For real-time systems, make sure to meet deadlines or else you're gonna have some data loss. And make sure process scheduling is regular to make sure your experience on the system is, well, up to par. If you're watching a video on a real-time system, you gotta make sure that, say, the audio and video are perfectly in sync. And now we get to the first two scheduling algorithms. And there are examples in the slides as well. The first one is called first come, first serve. This is the simplest non-preemptive scheduling algorithm out there. It's literally whatever processes we have, we do them in the order in which they arrived. Processes will run until they are completed with their job. Processes that enter the queue, enters a queue, by the way. So imagine processes falling in line in a queue. We run the first job in the queue, then we run the next one after that, and the next one after that. Processes basically wait for their turn on the CPU. First come, first serve. The advantage of this is that it's easy to understand and easy to implement. The disadvantage to this is processes must wait for their turn to run, and if a process is I/O bound, then it's going to spend more of its time waiting for I/O requests to finish. So if it's not doing anything on the CPU, so if an I/O bound process is running and we have a first come, first serve scheduling algorithm, then that process, when it's waiting for I/O, it's basically doing nothing. That would not be fair to the processes that are waiting in line. Really, if you want to be smart about this, what we want to do is remove the CPU from the process. So preempt the process. No, preempt the CPU from the process and let the next process in line run for a little bit. But this is a non-preemptive CPU scheduling algorithm. So we can't take away the CPU from a process, even if it's I/O bound, even if it's waiting for an I/O request to finish. We can't take it away. So that's the disadvantage behind first come, first serve. But there is a trick we can do. If we know how long each process will run for, we'll just sort all the processes so the shortest jobs run first. So shortest job runs first. We basically end up with an optimal algorithm here. So if we sort all our jobs by how long it'll take for them to run, we end up with an optimal scheduling algorithm. This is the best algorithm we can ever get. So why don't we use it? Well, we need a crystal ball for this. So, plenty of computer science thought experiments employ the use of a crystal ball. It is a theoretical device that lets us see into the future. And when we see into the future for these processes, we get to know how long they'll run for. Turns out, the problem is we don't have crystal balls in practice. This is information that we are unable to know. And because we can't know this information, we cannot implement this algorithm, SJF, in practice. It's not emphasized in this textbook, but is emphasized in a different textbook. We cannot implement SJF in practice because we can't know for how long these jobs will run. But it's great for benchmarking purposes. There is another one related to SJF, and that is called shortest remaining time next. If we know how much longer it takes for a job to finish, we can assign the process that has the shortest remaining time to be next. But again, much like with SJF, we need to know this information in advance. So that was 2 scheduling algorithms already. The next ones are round robin and priority scheduling. So round robin is one of the simplest, fairest, and widely used scheduling algorithms out there. Basically, processes take turns on the CPU. They'll run for some amount of time, and when time's up, they give up the CPU, so it's given to the next process in line. That process runs for the same amount of time, and when time's up, the CPU gives up the process gives up the CPU, and the next process in line runs next. This makes round robin a preemptive scheduling algorithm. And it's also the first preemptive scheduling algorithm that we are going to look at. So processes wait in line, they're in a queue. The process at the head of the line runs for some amount of time. We call that quantity of time a quantum. Once the quantum is up, the CPU is taken away from that process. The process goes back to the end of the line, and the next process in line runs next. So if we have a line with processes B, F, D, G, and A, let's say process B is currently running. Once time is up, process B moves to the back of the line, and now we have process F next. So the one thing about round robin is varying how long to make that quantum. So there is overhead related to context switching. Those steps of saving the values in the registers and then loading another process's values back into those registers. So those are steps. And that is overhead. And that means if we want round robin to be effective, we want to run our processes for as long as possible, so we minimize the number of context switches needed. On the other hand, we actually want a small quantum, so if this is an interactive system, it makes the system more responsive. So it's a balancing act of large quantums to minimize context switching and small quantums to make a system more responsive. And if the quantum is way too big, then round robin devolves into first come first serve. In practice, we would want something like 20 to 50 milliseconds for a quantum. Round robin. Now we're getting to our next scheduling algorithm. Round robin makes the implicit assumption that processes are equally important. Although it is a fair assumption to make, oftentimes this fairness causes problems if we have high priority processes. So, it may be the case that we need to run a mission critical job. We need to run this process without interruption. In priority scheduling, each process has a priority level, which whichever process has a higher priority level is the one that runs next. If a process has a higher priority than the other processes in the queue, it basically has first dibs on the CPU. It moves to the front of the line. If we have a preemptive scheduling algorithm and the process at the front of the queue has a higher priority than the process currently running, then not only does the high priority process move to the front of the line, it runs immediately. So whichever process was already running, we preempt the CPU. That process goes back in the line, and the high priority process starts running. Okay, so there are a few redundant slides in here, but let's go to an example. We have 4 processes, and we know how long they're going to run for. 8, 3, 15, and 5 milliseconds. If we use first come, first serve, then we run them in the order in which they arrive. Oh, by the way, we're going to assume that all processes here arrive at the same time in this order. So that means we're going to run process 1, then 2, then 3, then 4. For 8, 3, 15, and 5 milliseconds. We can calculate their waiting time and their turnaround time. So waiting time is basically how long they are waiting in the queue for, and turnaround time is how long it took from when they first arrived in line to when they finally complete their job. And we can calculate averages as well. So, okay, so let's think about this. So, process runs first for 8 milliseconds, process 2 runs second for 3 milliseconds, process 3 runs third for 15 milliseconds, process 4 runs fourth for 5 milliseconds. Each process waits some amount of time in the queue. Process 1 waits for 0 milliseconds because it was already in the front of the line. Process 2 must wait for 8 milliseconds for process 1 to complete. Process 3 must wait 11 milliseconds for the previous 2 processes to complete. And process 4 waits 26 milliseconds to wait because it had to wait for the previous 3 processes to complete. We can calculate an average waiting time, and in this example, it is 11.25 milliseconds. Using shortest job first, the first thing we do is sort all processes by runtime from shortest job first to largest job last. So the first process to run is process 2. After that, it's process 4. After that, it's process 1. And then after that is process 3. So they run for 3, 5, 8, and 15 milliseconds. What this does is reduce the average waiting time. So process 2, 4, and 1 were waiting for 0, 3, and 8 milliseconds respectively for their turn to run. Process 3 therefore must wait for 16 milliseconds, but once that time is up, once that time is up, process 3 runs. The overall effect of running processes in ascending order of runtime is reduced waiting time. And this is, as I said, the lowest possible waiting time. So in this example, we cannot get any better than 6.75 milliseconds. This is also far lower than our first come, first served example. So 11.25 milliseconds with FCFS, 6.75 using SJF. And we can draw what is called a Gantt chart that illustrates when each process runs. So you can just draw this on paper, or you can draw this up in Excel. We use a Gantt chart to visualize how long processes run. It gets a little tricky with round robin. Let's say for this example, we are going to run processes for 3 milliseconds at a time. Once again, we have our queue with processes 1, 2, 3, and 4 in that order. So process 1 runs first. So it gets a little bit interesting. Process 1 if we recall, runs for 8 milliseconds, process 2 for 3 milliseconds, process 3 15 milliseconds, and process 4 5 milliseconds. So process 1 runs for 3 milliseconds at a time. And then, after the 3 milliseconds is up, it's time for process 2 to run next. We know that process 2 runs for only 3 milliseconds. So once that quantum is up, it's already done. But either way, we then run process 3 next. It runs for 15 milliseconds, but it can only run for 3 milliseconds until time is up. Once that time is up, process 4 is next. So process 4 runs for, we know it's going to run for 5 milliseconds, but it can only run for 3. After that, we have P1 again. So P1 was waiting for its turn to run again on the CPU. So it runs for another 3 milliseconds, and then we go back to process 2. But process 2 was already done, so we go to process 3. So process 3 runs next for another 3 milliseconds, and then process 4 runs next for another. Here's what gets interesting. So we know process 4 is running for 5 milliseconds, but it only needs to run for 2 more milliseconds because it already ran for 3 previously. Process 4 finishes its job in 2 milliseconds before the time is up. In that case, we just let it go early, and process 1, which is already in line, goes next. So yeah, that's the one thing about round robin. Round robin means we don't let processes run for... Yeah, we do let processes run for a fixed quantum, but if it finishes before then that just means we can let the next process in early. So that's why we have little wedges here, these little rectangles. They're all size 3, but we have 2 little rectangles that are size 2. So process 4 runs for 3 milliseconds and then 2 milliseconds. After that, process 1 runs next for 2 milliseconds. We let process 3 in early. After that, process 3 runs for 3 milliseconds. When time is up, we let in the next process. But at this point, all other processes are done. So we just let process 3 run again. And again, to completion. So the Gantt chart is a bit more complex, but we can still count how long these processes were waiting for. Process 1 waited for 0 time to run the first time. The second time, it had to wait for 9 milliseconds. The third time, it had to wait for 5 milliseconds. So that's process 1. It waited for no time at all at this point. It had to wait for more time here. And, okay, I think there's an error here, but it's supposed to be waiting. Process 1 waits for 0 milliseconds the first time, 9 milliseconds the second time, and 5 milliseconds the third time. So that really should be 9, 12, 14 milliseconds. So that's a typo right there. So process 1 waits for that many milliseconds. Process 2 waits for 3 milliseconds because, well, it had to wait for P1's turn to finish. But after that, P2 finished at the end of the quantum, so it only had to wait for 3 milliseconds. Process 3 waits for 16 milliseconds because here's process 3. It had to wait for 6 milliseconds for processes 1 and 2, and then it had to wait 6 more milliseconds for processes 4 and 1, and then this many more milliseconds for processes 4 and 1 again. So 6, 6, 4, 16 milliseconds. Process 4 waits a total of 15 milliseconds because it had to wait for 3, 6, 9, 12, 15 milliseconds in the queue for its 2 turns to run. So if you calculate the average waiting time, it's not as good as SJF and slightly worse than FCFS. So this is the cost of making things fair. average time is not as good as SJF and slightly worse than FCFS. We can get different results depending on what processes we have waiting in line, by the way. This is just one example. We can make things more interesting by trying a smaller quantum. So for this extreme, let's try a quantum of 1. So process 1 has to wait for 0, 3, 3, 3, 2, 2, 1, and 1 millisecond for its turn to run. Process 2 must wait 1, 1, 1 milliseconds. No. My bad. That's 1, 3, 3 milliseconds. So it has to wait for a total of 7 milliseconds for its 3 turns to run on the CPU. Process 3 must wait 2, 2, 2. It's starting to get a little confusing, but look. All we gotta do is count how long P3 is waiting for. So 2, 3, 3, 2, 2, 2, 1, 1. So it has to wait for that many milliseconds. And then after that, it's the only process left in the queue, so it just runs continuously after that. Process 4 must wait 3, 3, 3, 2, and 2 milliseconds for its turn to run on the CPU. So that is a total waiting time of 15, 7, 16, and 13. And we can calculate an average that is 12.75 milliseconds. So all the different Gantt charts for different forms of round robin, and in comparison to first come first serve and shortest job first. We can also calculate a turnaround time, and we know all 4 processes arrived at the same time. So turnaround time is a time from when they... Turnaround time is how long it took to complete that process from the time that they arrived to the time that they completed their job. So for first come first serve, that turnaround time was 8 milliseconds. For process 2 in first come first serve, that was 11. Process 3, that was 26. And process 4, that was 31. For shortest job first, 3, 8, 16, and 31 for processes 2, 4, 1, and 3. Once again, much like how we can find an average waiting time, we can find an average turnaround time. Round robin becomes a bit more complex, but we just simply... For P1, we have it arrive at time 0, and it finally completes at time 22. For P2, it arrived at time 0 and finally completed at time 6. For P3, it arrived at time 0 and completed at time 31. For P4, it arrived at time 0 and completed at time 20. We can calculate a turnaround time off of that. It gets a bit more funky when we try it with round robin with quantum of 1. P1 arrived at time 0, finished at time 23. P2 arrived at time 0, finished at time 10. P3 arrived at time 0, finished at time 31. P4 arrived at time 0, finished at time 18. So it's a little bit... So really enough, we have some processes that have higher turnaround time and other processes with lower turnaround time when we compare these two round robin quanta with the same processes. So depending on the quantum we choose, it might affect our average waiting and turnaround times. So let's make things interesting by introducing priority level. Let's add a 5th process that runs for 4 milliseconds at a high priority. and let's say it arrives at time 5. We have the same four processes as before, but we have a fifth process that arrives at time 5 that has a higher priority than all other processes. Note that there are two varieties of priority scheduling. The first one is non-preemptive and the other one is preemptive. For preemptive priority, we take away the CPU from the currently running process if the process at the front of the line has a higher priority than the process that was running. For non-preemptive, the CPU is kept by the currently running process until it stops running. As far as the high priority process is concerned, preemption affects how soon it's able to run. The simplest way to implement this is as a variant of first come first serve. When a high priority process is added to the queue, it's brought to the front of the queue instead. And depending on whether it's preemptive or non-preemptive, it gets a CPU right away or has to wait for the currently running process first. So, in the non-preemptive scheme, process 5 arrives at time 5, but process 1 was already running, so it has to wait for process 1 to finish. There we go. All this does is shift all the other processes' times around. If we allow this to be preemptive, then process 1 is preempted the moment process 5 arrives. It gets moved to the back of the line, and process 5 runs for, I said 5 milliseconds? I guess it was 4. Okay, so process 5 runs for 4 milliseconds, and once that time is up, process 2 runs next, then 3, then 4, and then finally process 1 is allowed to finish. So, depending on whether this is preemptive or non-preemptive, in the non-preemptive case, we have a turnaround time of 8 for process 1, but that became 35 when we made it preemptive. So yeah, that is something that can happen if once we get to priority scheduling. There is another risk that we have with priority scheduling. If we have lots of high priority processes coming in, they all get first dibs on the CPU, and we have a bunch of low priority processes in line, we risk having starvation. This is what happens when these low priority processes are just waiting in line and watching all the high priority processes come in one after another. So all these low priority processes are basically just waiting their turn, possibly forever. So that's what is called starvation, when a process is waiting for a resource forever. If many high priority processes enter the queue constantly, then low priority processes may not have a chance to run, if at all. A solution to that is to simply just increase the priority of these low priority processes over time. Eventually, they'll have a higher priority than all the high priority processes, and then they get to run next. It's also possible to integrate priority scheduling with round robin. If a high priority process enters a queue for round robin scheduling, the CPU is preempted and given to the high priority process until it finishes running. So we can make a variant of round robin that implements priority. So if a high priority process comes in, it runs on the CPU until it's finished. If there was a process already running on the CPU, it goes back to the line and waits its turn again. We can add multiple queues, each one for a different priority level. In some cases, it's easier to have separate queues for different priority levels. Shortest process next. Interactive processes follow the pattern of waiting for a command, then executing a command. If each execution of a command is its own separate job, then we can minimize overall response time by running the shortest one first. This is basically shortest job first for interactive systems. One approach is to make estimates based on past behavior, and the process with the shortest estimated runtime. Yes, so we estimate how long processes run based on past behavior, and then we run the process with the shortest estimated runtime. Suppose the estimated time per command for some process is T0, and the next time it's run, it's T1. The runtime is estimated by doing a weighted sum between T0 and T1, where each weight is determined by a variable called A, Thus, the weighted average is A times T0 plus 1 minus A times T1. How we adjust A affects how we adjust A adjusts how much past runtimes affect the estimated runtime. Also, we can expand this to a weighted sum between any number of turns. This is the simple case of just 2 turns. Another scheduling algorithm is called guaranteed scheduling. It's based on a promise. Given n processes on a system, each process is guaranteed to get 1 over n of the CPU time. This requires keeping track of how much CPU time each process has had since its creation. So if a process has existed for 2000 milliseconds and it's one of 5 processes in the system, then 400 milliseconds of its existence should be CPU time. If this process had only ran for if this process that has existed for 2000 milliseconds and is one of 5 processes is entitled to 400 milliseconds of runtime, if we find out that process had only ran for 100 milliseconds, then it's entitled to more CPU time, just to make up for the fact that it had missed out on some compute time. If it had ran for 800 milliseconds, then it was entitled to more time than it was supposed to. We have an algorithm that chooses which process to run next based on... Okay, the process that runs next should be the one with the lowest ratio of actual time to entitled time. So, in this case, if we have our process that was entitled to 400 milliseconds of runtime, but only ran for 100 milliseconds, then it's likely to go next. A simpler implementation of guaranteed scheduling is called lottery scheduling. So it's much like guaranteed scheduling in terms of results, but with a simpler implementation. We give lottery tickets to every process. The system holds a lottery and each winner gets to run on the CPU. Processes may get extra tickets to increase their chance of winning. Cooperating processes may exchange tickets with one another. Generally, the process that has the most tickets has the highest chance of winning and thus has the highest share of CPU time. Also, we can apply this to other system resources, not just the CPU. Fair share scheduling is based on how many processes each user is creating. So let's say we have 2 users. User 1 creates 9 processes. User 2 creates 1 process. Then you would expect to split up CPU time so that user 1 has 90% of the CPU utilization and user 2 has 10%. Fair for the processes, not necessarily fair to the users. Or is it? What if user 2's processes were all CPU bound? And what if user 1's processes did very little work? Then, if we split up CPU utilization to be 90% user 1 and 10% user 2, then this would not be fair. So the problem is knowing what counts as fair and building up a policy based on that. To make things fair, the system can account for the number of users and give each user the same amount of CPU utilization. For n users, each user gets 1 over n of the CPU time, regardless of how many processes each user makes. But again, what if a user was running something that's compute bound? Or was running several processes that were all compute bound? Then that might not be fair, but you can tweak your fairness policy to account for these possibilities of user 1 creates 9 compute-bound processes, and user 2 creates 1 input I/O-bound process, or the reverse of user 1 creating 9 I/O-bound processes, and user 2 making 1 compute-bound process. So yeah, you have to tweak your fairness policy to account for these. Again, these are all different types of scheduling algorithms out there, but the ones that you're probably going to need to know are priority, round robin, SJF, and FCFS. Let's talk about thread scheduling. So if a process is multi-threaded, how threads are scheduled depends on whether user-level threads or kernel-level threads, or both, are supported by the system. With user-level threads, the kernel is unaware that threads even exist. The scheduling algorithm selects a process to run for some quantum. Within the process, there is a thread scheduler. That selects a thread to run until the quantum is up or no more threads can run, whichever comes first. So if we have a process that runs for 10 seconds, within that process, there is a thread scheduler that might decide, okay, thread 1 runs next, and then it runs for 3 milliseconds. Then thread 2 runs next, and it runs for 3 milliseconds. And then thread 3 runs next, and it, say, runs for 4 milliseconds. And then all three threads are done, but also the whole process is also done. So we can, at that point, we can context switch the entire process and run the next process after that. But what if we ran one thread? What if within that 10 milliseconds of allotted time for the process, thread 1 ran for 3 milliseconds, thread 2 ran for 3 milliseconds, but thread 3 had to run for 34 milliseconds? If the quantum expires with that thread running, the process with its current thread is preempted. When that process runs again, that thread will run again. So, if time is up for the process and a thread was still running, we just context switch the entire process. When we run that process again, that thread that was waiting to finish its job will run again. If the selected thread finishes running before the quantum expires, another thread of the same process is selected to run. So we have those 3 threads. Thread 1, the process runs for 10 milliseconds at a time. Thread 1 runs for 3 milliseconds, its time is up. Or actually no, it finished already. Thread 2 runs next, thread 3 runs after that. So if the selected thread finishes running before the quantum expires, we simply choose another thread to run. If multiple threads within one process run for short bursts within the quantum, they'll basically take turns based on a scheduling algorithm until the quantum for the entire process expires. In practice, this is going to be an implementation of round robin or priority scheduling on the level of threads. So it's kind of like a nested round robin. If we imagine multiple multi-threaded processes waiting in line, and within those processes we have threads also waiting for their turn. It's like round robin within a round robin. Yo, dog, I heard you like scheduling algorithms, so I put scheduling algorithms in your scheduling algorithms. Yeah, imagine how that would look like. At the process level, it's basically round robin, but within each process, it's round robin again. It's round robin within round robin, but the threads can only run if the process is running. So yeah, it's interesting to try to visualize, too. With kernel-level threads, the kernel selects a thread to run regardless of what process it was part of. That means it's possible for threads from different processes to take turns on the CPU. The selected thread runs for a given quantum until the quantum expires or finishes its work, whichever comes first. And we have a picture here to visualize what would happen. If we have user-level threads, then we could have thread 1 of process A run back to back until all the threads can't run anymore, or until time is up for the process. What cannot happen is the threads of process A and process B running after one another. So we can have the threads of process A alternate with each other, but they cannot alternate with the threads of process B. So we can have A1, A2, A3, A1, A2, A3, but we cannot have A1, B1, A2, B2, A3, B3. That cannot happen on a system with user-level threads, but it can happen on a system with kernel-level threads. So the main difference between kernel-level and user-level threads is scheduling. No. The main difference between kernel-level and user-level thread scheduling is performance. With user-level threads, full context switching is only done on processes. Context switching threads that are part of the same process does not require the same amount of work needed to context switch entire processes. Once again, context switching threads is easier than context switching processes as long as these are threads that are part of the same process. With kernel level threads, we might have to do full context switching on the process level if we end up context switching threads that are part of different processes. A smart enough kernel might instead context switch threads that are part of the same process before it even considers context switching threads from different processes. Context switching processes is more expensive than context switching threads. If you want to be more efficient with context switching threads, we want to prioritize context switching threads that are part of the same processes, before we context switch threads that are part of different processes. Again, it's like that round robin within round robin thing. So the final part of this discussion are two more IPC problems. The first one is the dining philosopher's problem. So Edgar Dijkstra came up with a thought experiment and came up with a solution for it as well. It's called the dining philosopher's experiment. Imagine 5 philosophers sitting at a table. There's 5 plates of spaghetti, one for each philosopher, and there's also a chopstick to the side of each plate of spaghetti. Of course, you know the rules about chopsticks. You need 2 chopsticks to eat. But there's only 5. Try not to think about that too much. So, each philosopher is either thinking or eating. To eat, a philosopher must take the left chopstick and the right chopstick, and then yum yum spaghetti. But the rule is this: a philosopher cannot take a chopstick that another philosopher has already taken. So no taking chopsticks from other philosophers. Yeah, it's forks, but I like the variant with chopsticks better because eating with 2 forks sounds silly. But the challenge, regardless, is to come up with a program in which philosophers don't starve. Starvation in the sense that not only are they deadlocked forever, but these are philosophers who are trying to eat and they just die of literal starvation. If a philosopher wishes to eat, the philosopher must call take fork on each fork one at a time. Once done, a philosopher must call put fork on each fork. So, take the left fork, take the right fork. Eat, put down the left fork, put down the right fork. So that is the sequence of steps that a philosopher must do when they want to eat. So, once again, take the left fork, take the right fork, eat, put down the left fork, put down the right fork. Sounds like a reasonable solution, but there is still the slim possibility that all 5 philosophers might want to eat at the same time. They each grab the left fork, but they can't grab a right fork because it's taken already to the philosopher on their right. And we end up with deadlock, and all 5 philosophers starve to death. Although this solution kinda works, it's not enough to guard against the possibility of this happening. So we need a better solution. So here's a more involved solution. We introduce semaphores into our solution. We have a semaphore, mutex, that is used to control access to the critical section. And we have a critical section. That is the part of the code where we take forks and put down forks. We have also an array of semaphores. This is used to block philosophers in case the forks were used. So I take the left fork, and I try to take the right fork, but that right fork was already in use by another philosopher, I tried to take the right fork, but I need to wait for that right fork to become available. We also have an array of states, so we're turning each philosopher into a state machine. So now we have different states. We have 3 states now. A philosopher is either thinking, is eating, or they're hungry. When, let's say it's philosopher 1. Philosopher 1 calls take fork, and down is called before we even enter that critical section. Once in, the philosopher changes their state to hungry and tests whether the forks can even be required. After testing, the philosopher calls up to release the mutex. When a philosopher calls down on its own semaphore, if the forks were not available, then the philosopher will be blocked until the forks become available. Once a philosopher returns from calling take forks, yum yum spaghetti. Once a philosopher is done eating, they call put forks to return the forks. This requires calling down to acquire the mutex before entering another critical section. Once in, the philosopher changes their state to thinking. And then, the philosopher calls test on the 2 forks to see whether there were any philosophers who were blocked because they tried to acquire a fork that was already in use. After leaving the critical section, the philosopher calls up on the mutex to release the lock. So the reader's-writer's problem is a different kind of IPC problem. The dining philosopher's problem simulates how processes use multiple instances of the same shared resource. The reader's-writer's problem is access to one resource. So we have a database and multiple processes that are either reading from the database or writing to the database. We don't have any issue with multiple processes reading from the same database. But if we want to write from the data, if we want to write to the database, the writer needs full exclusive access to the database. And no readers allowed, and no other writers allowed either. Only one process at a time is allowed to write. So one possible solution here is shown. The first reader to enter the database calls down on the mutex, and the last reader to leave the database calls up on the mutex. So we have a semaphore that keeps track of how many we have a semaphore that keeps track of how many readers and or writers are within the database. If a writer wants to make a change, it may not be admitted if the mutex is locked. In that case, it's suspended until the mutex is released. So the first reader that enters the database calls down on the mutex. The last reader to leave the database calls up on the mutex. At that point, the writer is allowed to enter the database. However, this can cause starvation on the writer if multiple readers are constantly entering the database to read. So an alternative solution is as follows. If a writer is blocked, any subsequent readers that enter the database are blocked instead. So, let's say we have 3 readers in the database, and a writer wants to come in. What the writer does is imagine the writer puts a closed sign out in front. So, right now, the writer is waiting for the last reader to leave the database. Meanwhile, other processes that wanted to read, they go to sleep. They are now waiting for their turn to enter the database after the writer has written. So, 3 processes in the database, 1 leaves after the other. The last one to leave signals to the writer that it's time to write to the database. the writer edits the database, and once the writer leaves, it signals to the waiting readers that it's now ready for reading again. Let me reiterate that once more. If a writer is blocked... Okay, so let's do that again. Let's imagine... Let's just go over it again. 3 readers in the database, and a writer wants to come in. The first reader that ever entered called down on the mutex, and the last one to leave will call up on that mutex. At that point, once all the readers have left, it's a little bit hard to understand. It can be a little bit tricky to understand, but when the first reader enters the database, it calls down on the mutex. Once the last reader has left the database, it calls up on the mutex. So, we have 3 processes in the database. They're all reading from the database. A writer comes in, puts a closed sign in front of the database to inform that other readers that they need to wait their turn to read. Eventually, all 3 readers leave the database, calls up on the mutex. The writer then calls down on that same mutex and edits the database. Once it leaves, it calls up on the mutex, removes that closed sign, and now the readers are allowed back in the database. So, hopefully I did this. Hopefully I did a good job explaining what is going on with the readers-writers problem and the dining philosophers problem. Really, the main thing that I wanted to talk about was the different scheduling algorithms. And this is, as I said, a primer for our next project, and that is a CPU scheduling simulator. So I'm gonna have instructions on that sometime next week, okay? Alright. If you have any questions on your current assignments and you wanna check in with me on that, you can either email me or meet me in class next Tuesday about that, okay? Alright. So, be on the lookout for instructions on your next project, hopefully to be coming in next week, and we'll take it from there. And once we're done, we're gonna move on to our next topic, memory. Right? Take care.